Chapter 4 is probability. And this tends to be the most challenging chapter in this course. Now, I don't want to be all gloom and doom. Some people love this and do much better at 4. The majority find it more challenging, and it's more like math. A lot of what we went over in chapter 1 and 2 and 3 are concepts and definitions. Well, now we're getting into some nitty-gritty mathematics. I only mention that by way of if you need to make an adjustment in your study skills and in preparation for this course, this is the time to do it. We're going to, this is our plan of attack in chapter 4. Notice that 4.7 is not included in our course syllabus. So I'll be skipping that. 4.8 Bayes' theorem, in your book, it just says, go see the CD-ROM. So you really don't have a chapter 4.8 in your book. Don't worry, when it comes to that, I have some supplementary materials and we'll go over that. But today, it's really the basic concepts of probability. That's where we're starting. Now, why is probability so important to us? Yeah, good question, huh?
It helps us make better decisions.
Boy, he's good. Read ahead the slides. Yes, it's my totally unbiased opinion that this is one of the most important math classes you'll ever take, not including 106, the next one. It's all about helping you to be educated consumers of quantitative information to help make better decisions. That's why we have statistics and probabilities at the core of statistics. And probability, it's something we all have this intuition about, but probably not real precise. And being in math class, that's what we're going to do. We're going to be precise about it. But before we get precise, let's just take a little pause here and let's think about probability. For example, I have the vast resources that VMI makes available to me. I have some tools here for teaching probability. Is that a penny? He confirms it is a penny. If I flip this, what's the probability it will be a hit? We haven't even defined probability yet. That is an English word. You use it. Now, Dinah, what's the probability?
50-50.
50-50. Anybody else would have said it differently? Yes.
You gotta see both sides of the coin.
He's a skeptic. Yes. Will you tell your colleague there's two sides, the heads and the tail?
There's 2 sides.
There's the 2 sides. All right, there. How else might you answer a question, what's the probability? What else would you say? Okay, Russell.
About the 50-50?
Yeah, if I flip a coin, what's the probability?
I would say 50-50, or I guess if there was another option more towards head side.
Okay. I was thinking you might say 50%, 1/2, or you might say even. Right? Different kind of ways of speech to talk about probability. Well, why would you say 50-50?
There's 2 sides.
2 sides. Okay, there's a heads or tails. Half heads, half tails, right? One or the other. I have a thumbtack here. I'm going to drop it, and it's on the floor. You got to pick it up because I don't get another one this semester. What's the probability of land on the point? It's either going to land on the point or it's not going to land on the point, right? It's either heads, it's tail. It's either going to land on the point or it's not going to land on the point. So, Mikowski, what's the probability? It's going to land on the point. You have no idea. You're an honest man. I appreciate that. Hamilton?
Also have no idea.
How would you express that probability, though? If I twist your arm and say, tell me, what's the probability that this is going to land on its point?
Did it stay on its head or just
Yeah.
land on it? It says 0.
0. What does that mean, 0?
It's not going to happen.
It's not going to happen, huh? Well, it didn't happen this time either. No. Now, those are kind of obvious, silly examples, but why is that different than a coin? It's either on its head or it's on its point or not. Something's different there, isn't there? In this kind of obvious example, there's something very different because with the heads or tails, we have this kind of trust. Some of us have this trust, not everyone, that it's a fair coin. It's only got two sides, and just our experience in the real world says either one is equally likely. But as soon as I picked up that pin and say, what's the probability of it dropping on the head, dropping and landing on the head, you knew something was different, didn't you? Two outcomes, but they're not equally likely. A lot of what we're going to be doing today, in the first bit of this, is learning to talk about probability more precisely so that we can distinguish between these kinds of situations and we can calculate the probability accordingly. Because not everything is the same. You use probability all the time in the world. Every time you cross the street and there's a car coming, you do a calculation. Right? Am I going to get across there safely or am I not? I don't know if you've started working on your 401ks yet, have you? Probably not. But a question I'm interested in is what kind of investment should I be making? Why am I concerned about that? Well, investments have different risks. Some vary a lot. I could buy U.S. savings bonds or I could buy penny stocks. What's the probability in 5 years that I'll have all of my principal plus a little bit more? Right? That's a sense of a probability. Take a more somber example here. You go to a doctor's office, hope this never happens to you. You have a test. It says, sorry, it came back positive. Does that mean you have cancer? Well, we're going to use examples like this. We're going to see you have to be careful how you calculate that probability. In some cases, it's not very likely at all you have cancer, even though your test is positive. Okay. Be careful about how you calculate the probability and what questions you're asking. Here's another probability problem. How can I design a computer network that's 99.999% reliable? And I guess VMI should be studying this problem, right? After our experience last week. How do you do that? That's a probability. How would I find out, how would I engineer something so it's 99.999% reliable? I mean, would you go on an airplane that was 95% reliable? Would you take a flight? Cheap fare, free movies? Probably wouldn't do it, would you? Maybe. All right. All right, let's continue this thought experiment with the goal of getting some language so that we can talk about these diverse sets of problems in terms of probability. And we'll go back to, the next few weeks we're going to be talking a lot about coins, dice, cars, and roulette wheels. Now, I'm not endorsing or recommending gambling, but they just happen to be great examples for calculating probability. And seriously, if you're not familiar with a deck of cards, it'd be a good time to become familiar. Using that example one. But let's go through three quickly here. I toss a coin once. What can happen? What's an example? What can happen? Well, I could get a heads. But what are all the possible outcomes from flipping a coin once? Well, there are just two of them. I could write them as heads and comma tails. That's it. All equal. Well, that's pretty simple. What if I look at a slightly different experiment? I'm going to toss the coin twice and record the results. Now, what's the possible outcome? Well, it could be a head followed by a tail. That's one example. But how many possible outcomes are there now? Well, now there's four of them. Just a tiny step, a little bit more complicated. I'm going to roll a dice once and observe the number that comes up at the top. 1 through 6, possible outcome is 6. But the total set of all possible outcomes would be the numbers 1 through 6. When we talk about probability, we need to have names for these things. So now we're going to give them names. An event. Any collection of results that are an outcome of a procedure. or an experiment. Events are what we're interested in probability because we're going to calculate probabilities of events. It seems kind of obvious, but actually it can be challenging sometimes just to understand clearly what is the event that I'm talking about. A simple event cannot be broken down further. We will not get to compound events for a few lectures yet, so I'm going to backtrack then. For the time being, everything we're working with are simple events. But you'll need to be able to distinguish later on between a simple event and a compound event because the rules we use to calculate probability are different. And the sample space is the name we'll give to the set of all the possible outcomes of simple events. Everything that possibly could happen when I perform this procedure or this experiment. Now let's go back to the previous slide and we'll fill in the correct names. This is part of our language now. When we talk to each other in this class, we'll be talking about procedures or experiments, events, sample spaces. Let's do one quick little practice here. My procedure is going to be observe a single birth and record the gender of the child. All right. Yvette Lombardi, what would be an example of the event for a single birth? Yeah, B. What would be the sample space? B or G. That's about all there is. For 3 births, now I'm changing the procedure or the experiment. Let's stick with you. What's an example of an outcome of that procedure, of event? BBB. BBB. All right, all of you take a piece of paper in a minute and think about what the sample space is for this experiment. See if you can write everything down. Sample space is the procedure of observing 3 births and recording the gender of the child. How big is this sample space? What's in it? Yeah, Arnold? Larry? No. Anybody got a list? You want to share? All right. Griffin?
BBB,
All right. BBB.
BBG,
BBG.
BGB,
BGB.
GBB, GBG, GGB, and BGG.
You missed one.
GGB.
So there's 8 possible outcomes in this sample space. Now that's with 3 births. You can see this would get kind of tedious if I said, well, let's study 10 births at a time. It might take a few hours back in your list all of those. But we'll come across ways of shortcuts calculating numbers like this and calculating the probabilities. All right, let's get down to brass tacks here. We've got some words. This is math class. Let's use some symbols. Mathematicians like to use this concept of a function. So the probabilities that we generate are considered functions. And we'll always use capital P to denote the probability function. Events, recall events are what we observe, and we're interested in the probability of events. So they're typically represented by capital letters. Later on, when we talk about random variables, we use the letter X. Typically, capital letters. And I'll say P of E will mean the probability of event E happening. That's what we mean. Okay, now, what is this thing called probability? Well, earlier when we talked about the flipping coin, we heard 50-50, 50%, even. Well, we have to come up with a consistent, meaningful way to talk about probability. And we're going to do it as simple as this. The probability of any event is always between 0 and 1 inclusive. And that's intuitive, and it makes a lot of sense mathematically, too. Probabilities for us are always between 0 and 1 inclusive. Now, I guarantee you at some point in time in this class or the next one, you're going to make a mistake in a calculator and end up with a probability greater than 1. When you do that, it will happen. You immediately know you made a mistake. There are no probabilities greater than 1. We interpret 0 probability as, well, we said it earlier when they asked about the probability of that thumbtack landing on the sharp point. 0 is, it cannot happen. It does not happen. Probability 1 would be, it's certain to happen. It will always happen. Then everything else is kind of in between. So our task in the next couple of weeks here is to understand a situation, what's the procedure, what are the events, what's the sample space, and based on all that information, come up with a number between 0 and 1 to represent that probability. Okay, that's our job ahead of us. There are 3 different ways that we will talk about computing probability. I think one of the biggest challenge in this chapter, it's really the math isn't difficult, but there's just lots of little nooks and crannies. And you have to be able to detect what situation I'm in and which set of techniques to use to get the probability. But the math here really is quite simple. Let's go over these 3, try to make all 3 today, and talk about them. First rule is relative frequency. And in this technique, I basically take a sample or a survey, and I count. And I count the number of times my event occurred, and that's the numerator. The denominator is the number of times I repeated my experiment or my procedure. Now that's a little bit abstract, so let's put some flesh to that as an example. Let's suppose I'm interested in finding the following probability. My procedure is I'm going to randomly select a cadet. Somehow I'm going to pick one of the 1,500 odd cadets. My event I'm looking for is I will observe that cadet and see if he or she has blue eyes. And I want to know that probability. Get it, Science?
Say the number of times they occur over.
You want to see that slide again? Sure. These will be up in Angel after the lecture.
Yeah, I got it.
All right? Now I'm going to give an example of this ratio. That's the kind of dry, generic, most general definition. Switch back to concrete example. I'm interested in coming up with a number that represents the probability of selecting a cadet with blue eyes. And in these cases, these are going to be estimates. And here's what I'll do. I'll select 80 cadets. And then I will observe how many of those cadets have blue eyes. And that will be my ratio that is in this previous slide. the number of times A occurred corresponds, in this example, to the number of blue-eyed cadets in my sample of 80. The number of times the procedure was repeated, that's 80. I sampled 80 of you. Now, let's take some examples. If I didn't find one blue-eyed cadet in 80, what probability would I assign? 0. Does that mean there are no blue-eyed cadets? No, it just means that the best estimate I can get based on my sample using the relative frequency method is 0. And if 40 of the 80 had blue eyes, my estimate of the probability would be 40 over 80.5. But whatever happens, you're going to get a number between 0 and 1. Okay? Relative frequency approach. And there's an example. Now, the second rule, the author calls the classical approach to probability. Please be alert to the second line. Requires equally likely outcomes. This is a big potential landmine here. You want to apply this rule in a situation where you can't. It's only applicable if the outcomes are equally likely. Going back to that thought I had, you really have to understand the situation. What nook and cranny have I discovered here, and then what technique is appropriate. So here, we're going to do this ratio, but it's a little bit different. The numerator and denominators are different. I'm interested in the probability of event A. So I look at all the different number of events that could occur. This is the size of my sample space, isn't it? Then I look within that sample space and see how many ways my event can occur. And I look at that ratio, and that's going to be what I call the probability of event A happening. All right, now that's the abstract definition. Let's do some examples so it makes more sense. Go back to our very simple problems. Let's go to the procedure. I'm going to observe 2 births. The event I'm interested in is exactly 2 girls. I want to know P of E, the probability in 2 births of having exactly 2 girls. All right, well, first of all, can I use this technique? What's my requirement to use this technique? I just admonished you to remember this. All outcomes equally likely. In this case, is it reasonable to assume that all outcomes are equally likely? Boy, girl, 50-50. I think in biology, us males might be favored by a little bit, I read, because we tend to die off faster, but let's assume for math, of course, 50-50. So equally likely I can use this technique. My event E is exactly 2 girls. So I would say E equals 2 girls. And I'd write that as GG. So I want to know the probability of that event. P of E equals S over N when the outcomes are equally likely. You're going to see that little equation a lot. It comes in handy. Well, in this case, what's the S and what's the N? My event is 2 girls. Here's my sample space. How many times in my sample space do I have an outcome that corresponds to 2 girls? Just once. So S equals 1. N is the total number of outcomes in my sample space. In this case, it's 4. So the probability I would assign is 0.25. Easy enough. That's making it more interesting. Same problem, but now I've changed the event. The event is at least 1 girl. That's the event. I still have the same outcome space because it's the same procedure. I'm observing two births. But now, how many events in my outcome space correspond, how many outcomes, correspond to the event at least one girl? Well, that doesn't, but this one and this one and this one do. So I have 3 of the outcomes that correspond to that event. And I still have the same number of outcomes, so now my probability is 0.75. Everybody with me? Just a little bit more interesting. That's the basic mechanics behind a classical rule probability. So one of our challenges is going to be, coming up, is how big is my sample space and how many ways can my event actually occur? The S. The equation is easy, S over N. What you're going to see is challenging. Well, how do I calculate S? How do I calculate it? Okay. Now, last bit of material here. Subjective probabilities. This is, in other case, when everything else fails, we use an educated guess. There's really no mathematical approach to this. It is just estimated by, hopefully, someone knowledgeable of the circumstances. So what's the probability that lightning is going to strike Mallory Hall in the next 24 hours? Well, is the relative frequency rule going to work here? What would the relative frequency rule look like for this probability? That makes sense, doesn't it? No. How about the classical rule? Now, I could, if I say, well, for the next 10,000 years, I'm going to observe Mallory Hall. And for any day that year that is struck by lightning, I'll count. And I'll count the number of days in the next 10,000 years it's struck by lightning. Right? I could do that. I'm using 10,000 years because I think it's going to take a while. But I could use the classical rule. But that's not very practical either, is it? In this kind of a problem, it's really a judgment. We all know that lightning doesn't strike a particular spot of the Earth very often. So what would you say? 1 in 10,000, 1 in 100,000, 1 in a million? It's a educated guess. That's what it is. There's no formula. There's no calculator function where you can put in P of lightning strike, right paren, and then hit calculate. It's not going to happen. All right, let's do a little practice here. Can you read on the left there? How's your eyesight in the back row? Is that Keys? Can you read that?
Not really.
Not really?
No.
Let me see if I can bump it up here a little bit. I want to look at some situations, and I want you to tell me which of those 3 methods we'd use to calculate the probability. Probability the next president of the United States is from the state of Virginia. How might you do this?
Subjective relative.
All right, we have an offer here subjective because
You can't really figure out the answer possible, so you something that would give back a little bit of information from past presidents.
okay, it could be just a guess. Could we use any of the techniques? Because, go ahead.
MA105 is equally likely outcome.
Are they equally likely outcomes? What about the relative frequency approach? What would that be in the context of this problem? Yes.
Could you look at how many Virginian presidents we've had?
Yeah. I mean, this might not be very sound reasoning, But the relative frequency approach would be, well, how many presidents were from Virginia? And quite a few. But guess what? That was back a long time ago. We had a good streak there going to the state. It hasn't happened recently. That might lead you to believe that that's not a good way to assess that probability. What else could you, another way, possibly? That's kind of a frequency approach. And actually, this goes along your method, Ted Sias, this equal odds. What if all of us are equally likely to become president? If you felt that was true.
Yes.
And how would you calculate it?
I would have the number of states that are possible.
We got 50 states, but there aren't the same number of people in each state. No, but if we adjusted it by population, you could say, well, what's the ratio of Virginians to the overall United States? And if all of us are equally likely to become president, I think that's a fair assumption, then that would be a possible estimate of that probability.
So you basically just said all of them are working away, so what's the correct answer?
Oh, and this one, it would either be subjective, probably it's subjective, right?
It is subjective.
But you could consider those other techniques. They have pros and cons to it. The one that I just offered to you is, do you really believe that it's equally likely that everyone could be a president? Well, if you did, then you could do it proportional to population.
So if we can explain why we think that, then it would become hard.
Sure, in this kind of problem, yes. All right, it's kind of in the gray area, but how about a cadet is left-handed? What approach would I use to come up with that probability? I'm going to randomly select a cadet. What's the probability that cadet's left-handed?
Relative.
Yeah, and how would I go about getting that probability?
Asking how so many cadets.
I'd take a sample of so many and say, how many are left-handed? So how many left-handed people do we have here? I know just two of us. Oh my, that's unfortunate for the rest of you. So here, it's less than 10%. We could use that as an estimate of relative frequency. We talked about wait, how about a roll of a single dice is an even number? Which method applies there?
Classical?
Classical, because I think it's fair to say all outcomes are equally likely. So once my event is, in this case, I get the number 6. What's my sample space?
1 through 6.
1 through 6. So P of E equals S over N. Oh wait, I wrote down the wrong event. The event was an even number. All right, what's S and N? How many outcomes correspond to the event in an even number?
3.
3. And how many are my total sample space? 6, so 0.5. And the last one, we'll end on this. A person will vote for a specific candidate. How could I, a relative? So an example, this would be opinion polls, right? Aren't opinion polls just estimates of probabilities? Take a sample, ask you who you're going to vote for, and I use that as my estimate of the probability that a randomly selected American is going to vote one way or the other. All right, I'll see you Wednesday.